This is the penultimate lecture. The next one will have information about the final and sum up. Our ranks are heavily thinned by COVID, but nonetheless, this is an interesting and new area that we're going to be talking about today. I'm going to be talking until the end, but anything that is left undone, there's material at the end, anything that's left undone will not be on the final exam, all right? So the last slide is literally the last slide, okay? There's nothing in the last lecture that's going to be on the exam. It's kind of a review. Okay, so I want to talk about how one can determine if climate change would cause future conflict and how much of current conflict it's causing today. And I'm going to look at a couple of things pretty quickly, which are case studies of antiquity and some modern case studies. And then I want to turn to a new body of work that's come out of econometrics in the last few years. Now, it's a cliche to say that causation is not the same thing as causality. And that's what's going to separate 1 and 2 from 3. 3 is about statistical correlations. So this is a common thing that people say, well, you know, correlation is not causation. Yes, but the corollary is that if the correlation is sufficiently strong and repeatable, it always points to a causal factor, all right? So it's just a matter of interpreting it right. And the interpretation can be tricky, and the example I have is this one. If you haven't seen it, this is a famous example from statistics where the British High Command in World War II, there was this thing called a Blenheim bomber, and they kept coming back all shot up, right? And so the brass made a plane diagram with every hole from every of a shell from every Blenheim bomber that came back, and they concluded that they were going to have to armor these areas, right? And so, but then somebody said, that doesn't sound right, right? So let's give it to a math geek. So they gave it to Wald, who was a statistician, and he said, no, that's actually the opposite of what you should do. You need to armor these places, okay? And it's because all of the bombers that were hit there never came back. All right, so it was an observer bias entirely that was causing this pattern. If you get hit in the places where the bomber returned, it's non-lethal. And so, in fact, they armored the opposite places. So this is my point about the High Command was correct that there was a correlation between bullet holes in the plane structure that did, in fact, point to causation. They just had interpreted it wrong. All right, so this is a very complicated diagram, and it's meant to just show you, it's sort of a collage of studies that have been published in the literature of case studies, mostly by historians, environmental historians, that tried to interpret big events in history to extreme weather events, okay? And the first one is the collapses in the Mayan Empire. 2 of the 3 here are after these major droughts in the geochemical record. Does anybody recognize this place? Anybody? Or how about the movie from which it is derived, from which this image is derived? So this is the Tikal in Guatemala. It's the classic Mayan city of Tikal. And that is the Millennium Falcon right there. And so that's from the Star Wars Episode 1, right? And this is at the end where, okay, if you've ever seen the Star Wars movie. Anyway, you should, if you ever get the chance, go to Tikal, because you can stand up on the top of these pyramids and watch wildlife. It's spectacular. The Mayans planted fruit trees all through the rainforest there. It's now 1,300 years later, but the fruit trees are still congregated there. So all the frugivores, all the monkeys and the toucans and the parrots and everything are just like flying around the canopy all the time. And so these platforms above the canopy are really great places to watch wildlife. There's a whole bunch of these, like that Angkor Wat supposedly collapsed after a major climate event. In general, conflict in China is associated with major droughts and heat and cold spells. Talk about in a minute about why that is. This is a pre-Incan civilization in Peru that's been attributed to, it's on the banks of Lake Titicaca, and its collapse is affiliated with a drought. This thing is if you've taken an art history class, that's a famous object. It's called the Royal Standard of Ur, which was an Akkadian city in ancient Mesopotamia. These chariots are some of the earliest depictions of wheeled vehicles, and one of the reasons you can tell, if you look closely at the horses, you'll realize they're all muzzled, not bitted. And that's because they aren't horses, they're actually onagers, which is another equid, mean as sin, bite your face off mean. And so they had to, this is before the domestication of the horse. And as the horse domesticated, people didn't domesticate onagers anymore. Anyway, the Akkadian civilization collapsed at the second biggest drought in recorded history, going back 5,000 years. And the heaviest and most severe drought in that region was the one that immediately preceded the Syrian Civil War in modern times. So this is perhaps the most compelling of the lot. Wars in China corresponding to cold events in Mongolia. Every time it got cold in Central Asia, where the steppe horse people lived, they ran out of fodder and went and decimated China as a result. Okay, so they came south whenever it got cold. So all the big Chinese wars with the Mongolians occurred at that time. So there are a whole lot of studies like that, each one controversial and tricky. And there are modern case studies as well. One of the best ones is a book that was actually produced here at Princeton about the Arab Spring in 2011, when the countries that are shown here all suffered serious civil disruption. And what happened was that worldwide crop failures caused food prices to spike. Wheat went from $4 a bushel in 2010, July, to $9 a bushel in 2011. And the crop failures came from extreme weather, drought in China, wildfires in Russia, extreme precipitation in Canada, and winter cold in the US. As yet, there's no formal attribution of this to fossil emissions, but these are the kinds of events that, in fact, are commonly attributable. Global wheat demand was greater than supply, and this is what caused the spike. And the countries in the Middle East and North Africa are the largest importers of cereals. You can see here the percent of your income that you spend on basic staples. And some of these countries, it's over 40%, all right? And if wheat prices, if those staples more than double, it means you literally have no money for anything else, right? And so people go crazy when that occurs. This is a correlation between an index of civil disruption of violence in rioting and the severity of food price spikes. There is a correlation there that I think points to causation. It goes back to the French Revolution. And so there's a lot of evidence, in fact, that these extreme weather events, in fact, caused the outbreak in the Middle East. At the same time, people who do case study work always say, oh, but it's multi-causal. This climate disruption is a threat multiplier rather than the cause. The rebellion's leaders weren't starving, right? It's not every country had a revolt and so on. And that's true. But it begs the question then, well, how big is the threat multiplier? Is it such a big multiplier that it's responsible for most cases of disruption, of rioting? Or is it so small that it only slightly increases the probability of such a disruption? So the statement that it's multi-causal is good case history social science, but it's not helpful in the sense that What you need to know is it big or small? Is it a dominant cause of violence in the world or not? The Arab Spring of 2011 was only one of 2 events in the region. The Syrian Civil War also began about the same time, March 2011, when Assad's forces fired on a protest in the city of Dara. And Syria was in the midst of the worst drought in history, worse than the one that collapsed the Akkadian Empire. And this drought has indeed been attributed directly to fossil fuels by a scientific study, and now several. The problem was that in northeast Syria, 75% of production of crops was eliminated, and 85% of livestock died. And so 800,000 people lost their livelihoods, and 2 to 3 million were thrown into extreme poverty. And so 1 million people in Syria all of a sudden became food insecure. Literally didn't have enough to eat. And so a whole bunch just moved to slums in the cities where they were really pissed off and easily organized. And so when that happens, it's quite common for something to ignite. And then there are political forces that come in where there are leaders that have other causes and that sort of thing. And now there are more than 500,000 people dead. And so, this tragic image of a child dead on the beach in Turkey is just a harbinger, perhaps then, of climate change refugees crises to come. And so many of the problems that we think of as geopolitical problems may in fact have some level of root in climate change that's already occurring. And the question is, how much? Is this a lot, or is this just a story that environmentalists made up? And so that's where this high-end statistical modeling comes in. So the first study, and this was weak social science when it was published, but the strong part of it was that some characters put together this thing called a Scad database, which was a database of 6,000 sub-Saharan African conflicts that are sometimes just district-wide, sometimes nationwide, but they had this gigantic statistical database. And then they could ask, do these things tend to occur during unusual periods of weather? And how much higher probability do they occur when the weather is weird than when the weather is normal? And so what they did was, in this plot from this paper here, is they fit rainfall anomalies. So this is wetter than normal, and this is drier than normal. Statistically, they fit it with a parabola centered at 0, which is weird. I mean, that's, if this was a statistic class, they just flunked. But the point is, they got this great big whopping signal. And what is the whopping signal? It shows that, if it's 2 standard deviations drier than normal, which you can think of as a 1 in 20-year drought, there's about a 40% increase in the probability of a conflict. And if there's 3 standard deviations, if it's a 1 in 100-year drought, the probability of conflict is doubled. And the same is approximately true on the other side. If it's really wet, you get an 80% increase. And so they got this great big whopping influence where it looked like a large fraction of the cases of extreme violence kind of waited until the climate was weird, and then they went off. Now, that doesn't necessarily mean that if the climate events never happened, there wouldn't be these extreme events. Because it could be that it builds up and builds up and builds up, and when the weather's bad, everyone goes crazy. But they would go crazy a little later otherwise. But if you look at the data, it's really hard to keep that hypothesis alive. It looks like you really wouldn't have these events if the climate wasn't weird. And it's because these probabilities get so high with sort of 1 in 100-year weather. And nobody sort of waits 100 years to get pissed off, more and more and more pissed off until they pop, right? They're dead before then. So this is called a cross-sectional study because the the character who did it, and one of the main ones is a guy named Solomon Shang, who's at Berkeley. He's a econometrician. And he's interesting. He has Princeton roots. I think like both parents or grandparents were like heads of the math department here or something like that. And in any case, he did a lot of this work early on. It was heavily criticized because he was comparing different cultures that are radically different. So different countries. He's just piling them all together. And asking, and so he's basically asking, are countries with extreme weather more likely to have violence than countries without? But he was getting these whopping big signals, all right? And he published some papers in Science and stuff like that, and it was considered to be a big deal. But he was heavily criticized because he wasn't controlling for the large cultural differences that might have been correlated, both with violence and with extreme weather that would somehow make a fake signal here, so that he might be misinterpreting it. But he kept doing it anyway, and there are like so many. Risk of leader exit. That means the leader has to leave the country. Number of violent events. This is risk of civil war. Yeah, risk of civil war. You see going up 40% when the temperature goes up a degree. Annual conflict risk of any conflict. Land invasion. Let's see, number of violent events. Crime rate per capita. Risk of inter-team retaliation. This is sporting events, okay? It's whether or not the team comes in and it hits you back if somebody hits them. And number of Hindu-Muslim riots, okay? So he did a lot of these. And this big group called the Climate Impacts Lab at Berkeley, and now at the University of Chicago, just cranking these things out constantly. And then they developed an alternative methodology to address their critics, which is shown in this slide. And you are not going to be asked to repeat this, but I want to just show you how it works. So, and this is basically just really fancy pants regression. But what they do is, instead of looking across all cultures, they look within any one country through time and ask, when there's an extreme event within this country, is it more likely that violence occurs or some other kind of event occurs? Now, in no country, almost no country, are there enough data to do this, okay? But if you take all countries together and look for the trend, the within-country trend across all countries, it's possible to borrow enough statistical strength to actually estimate these things, all right? And so this is now sort of cutting edge, but not exotic statistics. So the way it works is like this. I can't remember if I have no, I don't. Okay. So the way it works is like this. You have some climate variable, and this is like this trace through time is like the temperature getting high, low, high, low, high, low, high, low, zig, 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 right? Bunch of data. And you have it from, for example, two different periods. Early on, when you have one climate, and later, say, when you have another climate. But it doesn't really matter. Let's just think about this blue trace, which would be like the temperature trace, where that axis is temperature and that's time. And hot, cold, hot, cold, hot, cold with the seasons and zigzagging around on top of that. And you know that the distribution of weather, which is the blue trace, is climate. And that's the statistical distribution of the blue trace. If we had a second climate, like if we waited 40 years and did this again, then you might get a warmer climate, like climate 2, which comes from the red trace. You see that? So that's a weather signal in the zigzaggy line, and it's the distribution of those, the probability of a, say, temperature signal between two small bounds is given by the height of the curve. That's the climate, the statistical distribution of weather. All right, so then you hypothesize that there is some response function, that some social outcome variable like rioting, how severe the riots are from 0 to severe, that there's some social function that responds to weather of some shape like this, say this blue one. Just hypothesize there exists one. And then you could say, well, look, how would this function be? Well, when the blue is here, it would be there, and when the blue is here, it would be there. And you can use this function to turn that blue trace into a blue social outcome trace, okay? Where when the temperature here is at the bottom of the curve, the probability of, say, rioting is low. And when the temperature here is low, the incidence of rioting is higher. And that gives you a riot frequency trace through time, right? Again, this is hypothetical. We don't know the shape of this thing. And we can look at the probability distribution of that blue trace over here and compare it to data. Compare it to data on the time history of the social output variable, all right? So we get a prediction, and we have some social outcome variable which has a distribution, and we can say how well does this function translate our weather data into the probability density, probability distribution of the social outcome variable, like how severe the rioting is. And then you ask, what functional shape maximizes the fit between what we observe in terms of the social outcome and what we predict from the weather? And that regression is what you do within each country, but you do then all countries simultaneously, all right? So that's unless you've taken some statistics, that's going to be like a lot of buzzing words in your head. But the point is that there's a way to do this and to estimate, given the giant amount of data that's available globally, fairly sophisticated shapes for these functions. And so these are so-called longitudinal studies because they look through time. Oh, incidentally, if you get a difference between two climates in the shape of this function, that indicates some level of acclimation. In other words, the degree of rioting at high weather quantities, like warm temperatures, is not as severe in the warmer climate, right? Curve shifts to the right. So this is one way. You could also measure acclimation of a society, whether or not it adjusts to a period of warmth and people don't go as crazy anymore. There are, of course, other ways to measure acclimation. The best way to measure acclimation is to go, for instance, in Europe, the simplest way to see acclimation to heat events is to observe that they built all kinds of buildings and staffed them with people in heat emergencies to take care of people so they don't die. After the European heat wave, the European Union in every major city established heat relief centers where you can go during a heat wave. And so there was a much more severe heat wave in Europe than the 2003 one that killed 75,000 people, like, I don't know, a year ago, 2 years ago. And it killed like no one because they had all these centers, right? So that's the way you would normally measure acclimation is say, did anybody build any is there a seawall to protect from the sea level rise? The point is you can also detect acclimation from a signal like this, even when when the only change has been behavioral, when nobody built any hardware. Okay, so there are tons of these cross-sectional studies now, zillions of them, and longitudinal studies. And so this is one, came out in 2009. It looked at the trends in temperature and warfare. And the prediction, which has held on track since this thing was published, is that by 2030, 9 years from today, then the incidence of warfare in sub-Saharan Africa is going to be up 54%, okay? So that's a pretty serious problem. It means 1 in 3 wars in sub-Saharan Africa will be caused by the climate change by 2030. And that's one of the reasons why people say there are hidden costs of climate change. These kinds of costs aren't in any economic model, right? No, so somebody says, well, what's the cost of climate change? And what are the costs of the damages and the damage function, all the kind of stuff that Sarah Constantino talks about. Don't include any of these costs. Don't include the cost of the conflict. Don't include the lost lives, right? This is all sort of outside this sort of standard econometric, economic optimization modeling. This one was interesting because 2014, violent crime in the US, it predicts an increase in 180,000 rapes and 22,000 murders and 2.3 million aggravated assaults. People, it turns out, behave, criminally when it gets hot. So the mechanisms for the strong effects of climate on conflict are that the hardship from the weather makes the cost-benefit ratio of conflict less than that of business as usual for at least one group. This actually came out of a study. And for the life of me, I can't figure out the difference between that statement and the statement that weather somehow makes conflict go up, okay? I mean, I guess the only thing is the statement that it makes the cost-benefit ratio less than that of business as usual, right? That people think it's a good idea to riot, I guess. Harsh weather weakens the state's capacity to suppress violence. I think this is interesting, right? And I don't know how strong that is. And the big one, I suspect, is weather-induced migration and urbanization. I'm guessing that's the big one. But there are other possibilities. Like everybody could just decide that I'm suffering here. There's something wrong with this regime. There's always some impulse to resist. And now my impulse is higher because I see palpable evidence that they're not taking care of me. That's the first one. Second is that now's the time to get them because they're down and weak, right? Because the extreme weather weakened them. And then the third one is I have to leave. I have nothing to eat. I'm going to go to a refugee concentration outside some city and listen to whoever is standing on top of a crate and talking to me. Now, there are still some problems with this cross-sectional method, and I don't want to overdo this. So I'm not going to ask you about some of these about the next slide. So just watch them because otherwise you could easily lose the thread. So it's interesting that weather events can either be continuous, like temperature, or discrete, like a cyclone hitting, right? And the social response to the weather may in fact be delayed and may be long-lasting, or both. And it's going to have some shape, right? So it's not like, oh, there's a cyclone and behavior changes, and now tomorrow there's no cyclone and behavior's back to normal, okay? There are all kinds of time delays and durations and longevities built into these responses. And to do the job right, you'd really ought to be able to estimate those things directly from the statistical method. And it also means that your response at any one time is going to be, in some sense, influenced by not just the most recent extreme event, but the one before that and the one before that, potentially. And so these things could build up through time. 3 hurricanes in a row might be a lot worse than that occur right together. It might be a lot worse than the same magnitude occurring, 20 years apart. So there is a method for dealing with this, and it's called pulse response functions and deconvolution. I'll show you how this works in a minute, but these are examples of empirically estimated pulse response functions. Probably the single easiest one to understand is this one down here. Effects of a day greater than 80 degrees Fahrenheit relative to 60 to 70 degrees Fahrenheit in the United States. And this is months after the temperature exposure. And this is the birth rate and the birth rate anomaly. And what you can see here is that exactly 9 months after the lousy heat event, right, after it was hot, birth rates drop, okay? And so you know what caused, that's, human gestation caused this delayed pulse response, all right? And so the rest of them are like that. And these are just empirical examples of pulse response functions that have been estimated. This one is change in GDP per capita relative to years after a tropical cyclone exposure. It actually continues to worsen for over a decade, all right, in countries in the developing world. This is months relative to tropical cyclone exposure. Cumulative female infant deaths are climbing up with the same sort of, on a 5-year time scale. You know, there's a different pulse response there. This one is daily male mortality rate and days after temperature exposure. If it's greater than 80 degrees, it occurs on the day and drops to 0 after 1 day. You're being killed by the heat on that day. It's heart attack, heat exhaustion, something like that. It's greater than, less than 30 degrees Fahrenheit. Turns out there's a delay. Cold has a time lag associated with it, and I don't know why. I don't know if that's disease from being inside, right, to being confined. It's getting COVID right now, and this was obviously before COVID, it's 2009. Anyway, it's possible to estimate these pulse response functions, and here's how you do it. You hypothesize that, I mean, this is roughly how you do it, that there exists some pulse response function, like this is, 10 time units or 9 time units after some event. The social response kicks in and then slowly decays away. You assume that's to be the case. And then you assume that your current, the social response is the sum of the pulse responses from all the previous events. So here there was one at that time, there's one at that time, here there's one at that time. You sum them up. And then, so weather event 1 is occurring here, and then this response to it decays away. Weather event 2 is occurring here, response decays away. Weather event 3 is occurring here, it decays away. And so you get a predicted weather response that looks like that for the social output. And of course, you compare that to data. And you do that with the same sort of fancy pants regression, and then you choose the shape of this function so as to maximize the fit between the data and the model, okay? So that's what people do to estimate those, and these things are all over the place. There's lots and lots and lots of these. So it's possible to see, for instance, acclimation, mortality from cyclones increases more slowly in countries with frequent exposure like Japan. All right, so what's going on here? This is the maximum wind speed for a hurricane or typhoon. And this is the log of people killed over the population. So what's the death rate from the hurricane, all right? And the logarithm just means it's the same as the death rate. It's just a way to see the data easier. And in Vietnam, what happens is that you're much more likely to be killed by, 13 meters per second of wind than by 9 meters per second of wind. Philippines, not quite as severe, but it looks like this. And Japan, there's an increase, but it's extremely lazy. Now, has anyone been in a typhoon in Japan? Anybody been in a typhoon in Japan? Yeah. It's really easy to get into a typhoon in Japan. One of the things you can do is go there in the summertime and stay for 2 weeks, okay? And almost certainly you're going to experience a typhoon. They'll get like 20 storms coming ashore in southern Japan every single freaking year. One of the things, if you even looking at pictures of Japan, or maybe you can see them in your mind's eye, or if you go there, take a look and you'll say, trees look different in Japan. They look like they're part of a Zen temple, right? You have these images in your mind of trees. And one of the things that you're picking up on is that the trees look like a giant bonsai, right? They're really thick, and then they have this little crown at the top. And it is true that trees in Japan are thicker for their height than trees elsewhere. And it's because they get hit by so many typhoons. They've evolved to be stronger. So one of the subconscious recognitions of a Japanese landscape is a tree proportion that looks to our eyes as though it's anthropogenic. It's caused by people pruning it in a certain way or something, which is actually a response to high hurricane frequency. And as a result, the Japanese have gotten unbelievably good at responding. You know, the Hurricane Ida that turned Queens Boulevard in New York into well, there were whitecaps. I mean, you could take a kayak down, and it was like a significant whitewater event. That was like 5 inches of rain, I think, something like that, right? 3 inches in an hour, but 5 inches total. And in Japan, when you're there and there's like 12 inches of rain in 24 hours, it's like nothing, right? The whole country is set up for it. And so as a result, they have this very lazy function, and that is clearly an example of adaptation, all right? So this is one of the problems with the cross-sectional method we were talking about before, in that, you can compare this Japanese function you compare Japan to Vietnam, and you're really comparing apples to oranges because their social response functions are just fundamentally different, okay? And so that's the point here. And in this case, this lazy response function is a consequence of acclimation. This is a pulse response. GDP decrease to cyclones is prolonged, but weakest in countries with the most frequent exposure. All right, so what Solomon Shang did here is to compare quintiles of from the least hurricane in the places that have the fewest hurricanes, or cyclones, or a hurricane in the Pacific is called a cyclone. And so a hurricane is a form of cyclone. So when we say cyclones, we mean big tropical convective storms with winds in excess of 75 miles an hour. That's what we mean, okay? And so this is the place with the fewest, and the fifth quintile are the 20% with the most. The second quintile are between 20% and 40% at the bottom, and so on, right? And these are the pulse response functions, and what you can see is that GDP per capita declines in this weakest quintile after hitting a cyclone and continues to decline for 15 years, all right, before starting to rebound a bit. In the second quintile, it declines and continues to decline for 20, but the decline is weaker. And the third, fourth, and fifth, they're not statistically significantly different, all right? And so they basically don't decrease at all. There's no significant decrease in any of those. So this is the point, is that this is adaptation at work. And it's a way to detect what parts of society will naturally adapt to extreme weather and what parts won't, all right? This is acclimation. Mortality from heat decreases with average level of heat. So the impact of a day greater than 90 degrees Fahrenheit on mortality rate, and this is the coldest 10% to the hottest 10%, right? So few heat waves down here, many heat waves up here. Point is, if you're in a place with few heat waves and there's a heat wave, it kills people. And if there's a heat wave in a place with lots of heat waves, it doesn't kill people because society is adapted to deal with it. So this may not sound like it's also, yeah, we get better at things. This is the response of the death rate to daily average temperatures in 1929 to 1959, where there was a big increase, relatively large increase in mortality, a 1 in 1,000 people more, an increase in mortality from the best weather of 1 person in 1,000, and a big increase at high temperatures. But then if you look at 1960 to 2004, it's a much weaker response. And that's simply because of heating and air conditioning and stuff like that, right? So that's an acclimation through time. What's interesting for me, more than the cases in which there is acclimation, because you expect acclimation. People aren't stupid, right? What's interesting is where there isn't any acclimation. And one of the places, disturbingly, where there isn't any acclimation is in yields of crops. Agricultural adaptation, crop yield impacts, appear to be relatively impervious to acclimation. So farmers, it's weird. There are like drought and heat-resistant varieties. There are drought and heat-resistant crops. But farmers appear to be so conservative that over the runs of data we have, there isn't acclimation. And so this means that if you're a USDA, then you've got to try to figure out how to educate people in a different way. Because right now, farmers don't appear to respond to events that are coming more frequently and that are damaging them economically. All right? So you can puzzle your way through those. Sensitivity of temperature to rich versus poor nations' GDP. You know, we might think of this as a problem primarily of poor countries. And it is true that the poor countries are more vulnerable to extreme weather than rich countries. But one of the really surprising things about this whole body of econometric work is how big the effects are in rich countries. This one is the annual gross rate of GDP being depressed by annual average temperatures that are too low or too high. And it's true that the means are greater, of the effects are greater in poor countries than in rich countries. But these changes aren't statistically significantly different from one another. Rich countries suffer too. And it doesn't appear to be the case that wealth really insulates you. I've got a few other examples that I want to show you, and then I'm going to let you go. This guy, David Lobel, who's a Stanford food security expert, between 1980 and 2002, trends in temperature and precipitation lowered maize and wheat yields by 3.8 and 5.5%. Rice and soy were unaffected. And so this isn't a big impact, but it's something that happened over just 22 years, right? A 5% decrease in yield. And that's why, in fact, we're worried about food security in the tropics and extreme weather. The Schlenker and Roberts showed that predicted climate change by 2100 lowers annual yields by 63% to 82%. That is a big problem, all right? That is tropical famine. And so the reason that there's so much focus on agriculture and the reason people take numbers like the lower ones so seriously is that you can see the signals happening today. And you can also see that that farmers aren't adapting to the changes so far, okay? Relative to a world without cyclones, realized cyclones lowered the global annual growth rate of GDP between 1970 and 2008, that's 38 years, by 1.27 percentage points. Now that may not sound like much, but the annual GDP only grows 3%, okay? All right? So taking one of those three away is a big deal, right? And so if you look at the raw data right now, between 1980 and 2016, 36 years, the frequency of, and I showed this to you in the extreme weather, there was a slide in the extreme weather lecture on this, but between 1980 and 2016, if you look at Category 5 hurricanes, there's a 400% increase in their frequency, right? So they're 5 times more common than they were over that 36-year period. It's about 200% for Category 4. Category 3s are only up a little bit. Category 2s are the same. Category 1s are actually less common. And that's the intensification of storms without an increase in their frequency is what we've seen. Now, the climate stress tests that insurers apply to climate change. So reinsurers are the groups that insure the insurance companies. So insurance companies sell all these policies to, for instance, protect your home from hurricane damage. But the insurance company knows that if it's really bad, they're going to go bankrupt. So they buy insurance that then spreads that risk all over the world, for instance, okay? And that's called a reinsurer, an insurer of insurance companies. The reinsurers are the ones you really worry about, because if they go under, the whole system goes under. The reinsurance authority this year, the biggest regulatory authority, recommended that the climate stress test we ought to use is an increase in the Category 5 hurricanes by 35% relative to the long historical. When in the raw data, the real number is 400%, okay? So there's a great big gap between the financial stress tests that our whole financial system uses to try to assess its vulnerability to climate change impacts and what the observed is. And that's a problem, especially when you see something like this, where historically, tropical cyclones really do decrease global GDP already. And so as they become more severe, we could really expect serious economic impacts. And ultimately, you could imagine a systemic crisis, a financial tipping point where some sector in the economy investors lost confidence in, right? So this business of financial tipping points is unexplored almost within economics, but really gaining traction now. Predicted climate change by 2090 induces damages valued at 10 trillion in net present value today. That's a big number, okay? Just a couple more. Realized typhoon-induced economic deaths account for 13% of the overall infant mortality rate. That's amazing. These delayed typhoon deaths are 13% of total infant mortality. And I think that's the last one I have for you. So we're within a minute of the end of time. So thanks a lot, and I'll see you. Thanks for listening, and I'll see you on Monday. Stay well until then.